All right. Hi, everyone. My name is Ron. I'm going to be your moderator today. Probably all that I'm going to do is call your names and tell you when the time's coming up. So if you'll do me a favor, when you're presenting and sharing screen, make sure you have the chat tab open. I know it's hard to get to, but that way you'll see when I give my warning. And I obviously don't want to have to tell anyone to get off the stage. So another thing is I always do this when I'm moderating a meeting. If you're presenting later, obviously, and you feel that there's questions you want to be asked, send them on to me, because otherwise I will try and make something up and it might not be a good question. Otherwise, thank you all for coming. I'm glad you're all here. Our first presentation is from Aleksey Ogulenko, Itzhak Benison, Cura, Josh Ost, and Aleksey Sinitsyn. I'm very sorry for everyone's name that I'm going to mispronounce today. Hopefully it'll be consistently mispronounced across everyone. The presentation is the fallacy of the closest antenna towards an adequate view of device location in the mobile network. I can see one of you is here. Aleksey, are you presenting today?
Yes, I'm presenter.
Right. Please do take it. It's great to see you.
Glad to see you too. Okay, I will try to share my presentation. Okay. Is it okay? Can you see my presentation now?
Yes, that's great.
Okay, thanks. Thank you for introduction. I'm glad to present today our research on positioning using mobile phone data. We did the first part of this work at the Geosimulation lab of Professor Itzhak Benison in collaboration with Professor Isaac Omer, Department of Geography, Tel Aviv University. The second part became possible thanks to our colleagues and friends from Sweden, Professor John Ost and Dr. Marina Toger. This study was inspired by permanent need in the data on human mobility for the transportation modeling, and also by the simple fact that mobile phone companies don't want to share this data, mostly due to the privacy concerns. The main source of information about when, where, and how people communicate through the network, mobile phone network, is a call detail record, CDR for short. It's basically a data record produced by the network's equipment to document meta information about the connection. And usually the CDR data are available to researchers in aggregated or censored form only. CDR may sometimes contain measurement of the distance from the device to the cell tower based on time in advance or signal strength measurements. Even more, mobile operator may equip the CDRs with the location field, like on the slide, but it's hard to say what this field means exactly. Usually it's just the cell tower's location. Over the last 30 years, the broad view on positioning using mobile phone data was established based on the Voronoi tessellation. This approach assumes that at the time moment recorded here in CDR, the device is located within the tessellation polygon of the cell tower, also written in the CDR. Actually, the word cell in cell tower refers to this concept. So what consequences such view on position implies? Let's consider one of the basic scenarios of attack on location privacy using the concept of Voronoi polygons. The idea of disclosure is based on the assumption that persons' locations in space are in one-to-one correspondence with Voronoi polygons. We assume that the adversary has access to the anonymized CDR database. Anonymization doesn't help here much. And also adversary can surveil the target person in real life, in real space. This attack starts with observing the target person during a communication event, such as a call. Then adversary determines a Voronoi polygon which covers the target's position, and thus she gets to know the corresponding antenna or tower ID. Knowing this antenna's ID, adversary queries the database for all CDRs recorded during the observation interval, and obtains set of devices IDs written in these CDRs. Adversary believes that the target's device ID has to belong to this set. So she repeats this process of observation of surveillance a few times until only one device ID remains common for all sets. And this will be, adversary believes, the device ID of the target person. Knowing device ID of the target person, adversary can recover all mobility history, call history, all information, private information from CDR database. There is a well-known estimation, you can find it even in Wikipedia, that only 3 to 5 positions are sufficient to identify almost any device in the network by such attack. So only 3 to 5 observations in real space are sufficient. However, what these and many other scenarios and studies ignore is the coverage overlap of the coverage areas of antennas. Recently, doubts in tower-based Voronoi partition resulted in few essential modifications, yet the main idea of non-overlapping tessellation remains the same. One may ask when all it started, when this view became dominant. Well, the earliest document we found about coverage area partitioning is this technical memorandum on the left of year 1947 under the title Mobile Telephony, Wide Area Coverage. It summarizes the Bell Labs research on the most efficient regular pattern for radio frequency reuse. The problem with radio communication and mobile phone communication is that it's very hard to carry on few conversations at the same time in the same direction and using the same or close frequencies, because transmissions simply interfere with each other. For technical reasons, mobile telephony equipment cannot use too many frequencies. So it needs to reuse the available frequency bands in the most efficient way. Author of this technical memorandum proves that a regular hexagonal pattern is the optimal one, and moreover, he describes possible configuration of such network for New York metropolitan area. 30 years later, this idea was revived. This time, Bell Labs had both need for this technology and scientific and engineering capacity to develop it and deliver it. The article Advanced Mobile Phone Service, the Cellular Concept by McDonald, was published in Bell Labs Technical Journal in 1979 and described the cellular system almost exactly as we know it now. Particularly in this paper, McDonald writes, it's not possible to precisely define a coverage area for a given cell site, in the sense that site never serves mobile units outside the area and always serves mobile units within the area, within the coverage area. So 40 years ago, McDonald was aware of the coverage areas overlap and problems that it applies. Obviously, pure hexagonal coverage, like on this slide, becomes impractical in real heterogeneous urban environment, and 20 years later, it was substituted by its direct generalization, Voronoi tessellation. The earliest use of the Voronoi tessellation that we found came from France Telecom in two papers, 1996, 1997. Bocelli and others proved that Voronoi coverage is more suitable for optimal frequency reusage than a hexagonal pattern. The most interesting, they write directly, we take the assumption that subscribers are served by the closest antenna, by the closest station. And eventually this assumption became an axiom that everyone believes in it. This model based on non-overlapping Voronoi polygons is quite appealing. It is simple, it is deterministic, not like something on this line right now. It's beautiful in mathematical sense, people simply like it. But Voronoi model ignores valuable aspects of the network's workflow. You can see on the slide the overlap between two distance antennas located at the large distance, about 50 kilometers, and the overlap of the three neighboring antennas. Coverage area inside the sector of antenna is divided into ring segments, which we call trip-time bands, TTB for short. TTB's width increases with the distance from the antenna location. It varies from about 200 meters to 2.5 kilometers, and the maximum radius is 32 kilometers. At close distance, antenna's interference leads to reshaping of the coverage areas, which start to differ from the original layout, as suggested by Voronoi tessellation. In our study, we got access to the data on antenna's communication load, to the accuracy of these ring segments from one of the biggest mobile phone company in Israel. And here you can see three examples of so-called peerage curves. Each curve represents the number of connections performed through the certain ring segment, that is, at given range of distances from the antenna. And it is total number of connections during 1 month. Such curves are measured on a regular basis for internal companies' purposes. So in some sense, it's cheap data. Companies always has such kind of data. As you can see, curves vary in shape and demonstrate different patterns of coverage. One antenna serves connections close to the tower. Another one mostly covers an area at the distance of 2.6 kilometers. Equipped with peerage curves, we have developed a probabilistic model of positioning using Bayesian inference. In this model, this special resolution was defined by a regular grid. We split it the whole area, whole territory of the country by regular grid with a side length 250 meters. And basically what we did is the direct application of the bias theorem. We have an assumption of a device location with accuracy to small square grid element. We have a posteriori information from peerage curves about how devices actually communicated with the network at different ranges of distances. And thus we calculate Bayesian estimates of the probability for the device to be located here if device has communicated from through the given antenna A, which is written in the CDR. In the network we investigated, there are almost 3,000 of towers, 22,000 of antennas. Each antenna has 40 trip-time bands, and we have constructed probabilistic location clouds for every cell tower and every single antenna in the network. Here you can see several examples of such clouds. They vary in size and shape. Clouds may consist of a few grid elements only, like clouds H or F. It can have a hole inside it. It can be even discontinuous. And this picture differs hugely from rigid deterministic partition of the area between non-overlapping polygons, as it is for the Voronoi model. As we find out, in about 3% of cases, the tower's Voronoi polygon does not overlap with the cloud at all. That means that there are almost no chances for the device to be located within the polygon. In another 3% of cases, on the contrary, Voronoi polygon covers the cloud entirely. And between these extremes, the remarkable result is that half of all Voronoi polygons cover less than 40% of the cloud's probability. So the area where device can be located in reality is much larger than it is from Voronoi-based view. Another example shows the Voronoi polygon that covers only small part of the entire corresponding cloud. Polygon comprises around tower A, comprises approximately 75% of the overall location probability. And the whole cloud is much, much larger. Obviously, the more grid elements we include in the cloud, the more fraction of the probability it cumulates inside. And typically in this network, an average 50% cloud needs to grow 9 times in size to cumulate almost all probability. Until recently, however, we didn't have objective measurements of location and human mobility to check our views. We have only data from mobile phone company. This year, we started to study another data set which allows us to compare GPS trajectories with mobile phone positioning. It's based on the data from one of the Swedish mobile phone operators and GPS tracks of few volunteers. The volunteers' GPS trajectories were recorded on occasional days during the last 3 years when the volunteers activated GPS recorders on their phones or special GPS trackers. Overall, we obtained tracks for 130 days. 68% of GPS locations were recorded within the borders of Uppsala municipality in Sweden. In the next step, we measured discrepancy between corresponding GPS points and CDR-based locations using both direct distance in kilometers and distance in Voronoi rings. We define Voronoi ring of order K for a given polygon as a set of its neighbors of order K. The CDR data were available to us in partially aggregated format. For every 5-minute interval, we had a list of cell towers that served the phone connections. During this 5-minute interval, a device can be connected to a single cell tower or switch between multiple cell towers. In the first case, we can determine the distance between each of the GPS locations within this interval and a cell tower. We can get both minimal and maximal distance, optimistic and pessimistic estimations of the discrepancy between GPS and mobile phone data. However, if the device was connected to several cell towers during the interval, we consider the minimal distance only to be on the safe side. The reason is simple. We don't know the exact moment of switch between towers in this case, so we don't know distance to which tower we should measure for every GPS point. Analyzing these conservative estimates of the distance, we found that only 37% of GPS points lay within the Voronoi polygon of the corresponding antenna, and almost the same number of points lay within the first ring of polygons, which has a much larger total area. And naturally, some locations are visited much frequently than others. In our experiment, we considered closely home and work locations of the volunteers. It appears that the home one location is almost exclusively, in 90% of cases, served by one cell tower only, and this tower belongs to the second neighboring ring of the Voronoi polygon that covers the building. The home 2 location is served by the tower in its first ring in 96% of all cases. Connections from the work location, which is common for our volunteers, are distributed between several towers, and this situation deserves a closer look. 3 cell towers denoted T1, T2, and T3. Connections are distributed between them. And I'm speaking about towers, not antennas. Each tower bears several antennas, 3 to 12 typically. So for one tower, you can have different antennas ID in CDR's database. As you can see, Voronoi polygon of the tower T1 covers the building entirely, while 2 other towers are located in the first neighboring ring of this polygon. And approximate domains of devices whereabouts, these areas on the right colored according to the tower of connection. These areas overlap heavily. It shows that connections from a certain location are not necessarily served by the closest antennas. No, the serving antenna is assigned based on the network state at the moment of connection. Moreover, antennas of several cell towers can serve connections from the same location. These simple observations destroy the idea of rigid coordination system based on Voronoi coverage of the network. And now, if we go back to the attack scenario, we see that set of CDRs, set of devices IDs among whom the target can hide is way much larger than it is for traditional Voronoi model, because the measured position of the target belongs to location clouds of many antennas at the same time, 12 antennas on average. And it looks very unlikely now that 3-5 locations observations are still enough for identification. The adversary needs to gather much more information to identify the target. So the former estimates of privacy risk cannot be taken on trust. Almost half of the towers, Voronoi polygons cover less than 1/3 of probabilistic location cloud. So the level of uncertainty in location is much higher than we can imagine. And field experiment showed that 2/3 of all connections are served not by the closest antenna, but the second, third, and so on up to the 6th closest antenna. I would sum up our findings in one sentence. The Voronoi-based approach to the location cloud, to location privacy is overcautious. We are convinced that the mobile phone data should be more available to researchers, since the controlled and careful revealing of them brings much less risk for mobility privacy than we and mobile phone companies used to think. Thank you very much for attention. That's all.
Thank you. Thank you very much, Aleksey. That was really a great presentation. I want to keep us moving though. Discussion will be at 10:40. Please stick around if you have any questions for anyone. It's not there. Our next presentation is from Natalia Zdanowska in Malta. Are you guys ready to present?
Yeah, and I'm going to share my presentation because I also send around a recording, but I'm going to present like in real.
That's great. Keep the chat tab open as well. Just a reminder.
Yeah, open chat. Yes. Just let me share the screen. Can you see my screen?
Yes, looks nice and clear.
Okay, great. Good morning, everybody. My name is Natalia Zdanowska, and I'm a geographer. I'm at the moment a research associate at the Luxembourg Institute of Socioeconomic Research, but I'm also a honorary research fellow at the Center for Advanced Spatial Analysis at University College London. And I'm telling you this because I'm going to present a work we've started back to when I was in London, and it's a paper or a draft of a paper which we wrote jointly with Robin Morfitt at UCL, and it's about the northern cities of the United Kingdom, firm ownership links, productivity, and interconnection. To give you a little bit of context, it's needless to say that the United Kingdom is a very centralized economy. It's a very centralized city system, where London is the biggest attractor of the main economic activities and also of the population. Manchester, where we're all supposed to be today, is the second economic center of the country. It has a lot of history back to the 19th century. It was in fact one of the most industrialized city in the world. It was the city that was also firstly connected by rail in the world. So Manchester is the second economic center, and but there is still a great imbalance, right, between London and the rest of the cities. And to tackle this, there has been several decentralization initiatives in the United Kingdom, and the Northern Powerhouse Strategy is one amongst them. So it's a government initiative which was launched in 2010 and 2016 to rebalance the economy of the UK. And one of the objectives is to strengthen the economic interactions between the cities of the north. And you can see on the map on the top that the cities that are included in what's called the Northern Powerhouse Strategy are mainly Manchester, Liverpool, Sheffield, Hull, Leeds, and Newcastle. And so these are kind of big challenges of the UK to rebalance the economy, and it's still on the government's agenda, given the Brexit and also the coronavirus pandemic, which also questioned the role of the cities outside London, because, well, there's a lot of people that were living in London, right, to the northern cities. So this is still a kind of a hot topic. Right, so the framework for this work is the system of cities approach. As Professor Luis Betancourt yesterday mentioned, there was a discussion about how to be working across scales, right, between macro, meso, and micro. And so this given work is concentrated on the macro scale, where cities are considered in a system, in a national system, and there are different problems that occur in such a system, as asymmetrical information and different relative position of cities within this system. So given this framework, the main research question that we formulated is, how does Manchester, but also the other cities of the Northern Powerhouse Strategy I mentioned, position evolved within this interurban economic networks in this highly centralized city system following the launch of the Northern Powerhouse. And the hypotheses we formulated are the following. So firstly, have the stated central and local policies of the Northern Powerhouse given rise to any subsystem in the north of the UK, which is observable and that we are going to observe at the level of these interactions between firms at city level. Then secondly, does the post-2010 industrial structure of Greater Manchester demonstrate a certain shift away from its traditional manufacturing base? And thirdly, which is a broader question, does the economic structure or the northern cities taken together offer a counterweight to the dominance of London? So to answer to this hypothesis and to the research question, we based our work on a very specific data set, which is the Orbis database extraction. So this is a data set which is produced by the Bureau van Dijk. And here I would like to thank the University of Lausanne to giving us the access to the extraction for the UK for 3 years, 2010, 2013, and 2016. So to give you a bit of an overview, this data set has a lot of negative and positive points, and amongst the positive points is that its strength is to give the access to the exact names and locations of the owners, of the owner companies and the owned companies. So in this and for these owners and owned companies, you have the exact activity codes, you have their turnovers, and you also have the characterization of the link that is linking both owner and owned companies, which is the percentage of ownership. So given the structure of the data sets, it is very easy then to apply a network approach to these firms. And this is why we defined the economic network of ownership links in the following way. So this is just an example of ownership level of firms at city level. So a firm A, for example, in Paris at level 1 owns a firm B in Manchester at level 2, and the latter owns another firm C, for example, in Singapore. And all this is defined by an ownership which is superior to 50% of ownership between firms. So this is an example of a 3-level ownership network. And then, so my presentation is not moving. Now it's moving, okay. Then the other part is to work at city level, right? Because it's about urban ownership links. This scheme illustrates that, for example, if at level 2 we have a common city, which is V1 in blue, then I proceeded to an aggregation of the city, and then we have what I called a multi-level ownership network. Okay, then there's another step, because what is interesting in this kind of network is not only to look at centrality measures and all these kind of things, but also the geographical scope of ownership. And in the given context, as we are working on the UK, so here we have at level 1, for example, firms that are in London, right, which own firms that are in Manchester, and we always have Manchester at level 2, and then these firms in Manchester level 2 can own either other companies in Manchester or in London or other UK cities or outside the UK. Okay, so coming to the geographical scope of ownership here for 2016, the main observation is that ownership is in this context very nationally driven, right? So 75% of owners in Manchester, they come from the UK, and in 45% of cases from Manchester itself. And then Manchester as a city where owners are located is also owning about 60% of other firms in Manchester and 85% of firms in the UK, right? So it's a very nationally driven network if we look at Manchester, and it's also very London oriented. So it's Manchester and then it's London and other UK cities. But what is interesting, is that Manchester here in red as a location of owners. These owners they possess at least 18% of these links in other UK cities. So this is a first interesting result in terms of this Northern Powerhouse strategy, which is, if you remember well, strengthening these interactions in the north, right? And then when we look at this geographical scope through time, one of these interesting results is that extra-European owners of firms in Manchester have more than doubled between 2010 and 2016, so from 7 to 16%. And then when we look at owners in Manchester owning other things outside, these other UK cities orientations has also more than doubled. So this is very in phase with what this Northern Powerhouse strategy, public policy, was tempting to achieve, right? Is to strengthen interactions of a city as Manchester with other UK cities of the north. Right, but this is these interpretations are made in terms of number of links. And there is a huge debate, at least in economic geography, for people that work on firm networks is what is the best indicator? Is it to look at the number of links, or is it to look at the monetary value of these links? So if we look at the monetary value, so the strength, what they call the ownership revenues that are generated by these links, they look pretty stable between 2010 and 2016. So these are two maps representing just links between the four biggest cities of this northern powerhouse, and it's they are rather concentrated on the largest urban centers. So this conclusion regarding something happening in the north is true in terms of number of links, but they are still very weak. And if we look at the monetary value that is generated from these links, it's pretty stable in time. So there is no big boom between 2010 and 2016. And in fact, if you look at these two maps, which are not appearing very well, but on the left you have all the companies that are owned by Manchester in the UK, and on the right side you have all the companies in London that are owning companies in the rest of the UK. You can see that there is a very clear imbalance, a huge gap between the economic power of London and economic power of Manchester as being the second economic center, right? Okay, so a last important result I want to show here, because I don't want to make this presentation very long, is that we looked at, apart from the structure of this link, we looked at the economic specialization of these northern powerhouse cities. And in order to look at this, we conducted a correspondence analysis on a matrix of cities and industries, or sectors, whatever you want to call it. And at the crossing of these metrics, there were the ownership revenues generated by firms in these cities. And then you can conduct this kind of correspondence analysis through time. So if you look at the representation of the first factorial axis here on the left, you can see the evolution of the specialization of Manchester, Liverpool, Leeds, and Newcastle. So what is interesting, if you look at Manchester in 2010, is that it has shifted. It has shifted from specialization in manufacturing to specialization in wholesale and trade, which is the letter G, to professional and scientific technical activities, which is the level M. So it's the arrow in red. And then there's another, so this is meeting in some way what the Northern Powerhouse strategy objectives were, but also what the objectives of the Greater Manchester Combined Authority industrial strategy was. So it was to upgrade the specialization of this city towards more scientific activities. And this is also confirmed by the GMCA's industrial strategy objective to create a graphene city, because the University of Manchester is a specialized, amongst other things, but in this production of graphene. So this corresponds in some way to the reality. And then if we look at another example, so for example, Liverpool here in green, there was also a very interesting upgrade in the global value chain, as firms owning capital of other firms have converted from agricultural, forestry, and mining, which is the letter A, in 2010, to professional and scientific activities, M, also near Manchester. So this is also a very important shift in this traditional manufacturing base. Right. So to conclude, to conclude for this presentation, our work has shown that there are some regional patterns that have emerged in this 2010-2016 period, which can be observed at the level of number of links. But in terms of economic weight and counterbalancing London, there is, for the moment, no real subsystem in the north of the UK. And we can kind of say that the Northern Powerhouse impact is weak in terms of offering a countering to the dominance of London. And of course, there's a whole debate related to the fact that maybe this Northern Powerhouse strategy is just a public policy which has been launched but not really put into practice. But what we observed is that the post-2010 shift away from the traditional manufacturing base has been made towards more advanced manufacturing, research and health in the case of Manchester and Liverpool, as I commented before. But of course, this is all a reasoning. I mean, in terms of its ownership links, right? It's not representing all the type of firms that could be present in Manchester. And to end, there are some possible extensions that could be made for the Northern Powerhouse assessment by linking these results with transportation interactions, as at the origin, the Northern Powerhouse strategy was also oriented towards these transportation links. And it was launched at the moment where there was this project in the UK of the high-speed rail 2, which has never been put into reality because of a lot of political problems and different economic contexts. Right, and we have been also undertaking currently some work to link these results with productivity measures, because there is a huge debate in the UK about the productivity gap between regions. But what we want to do is to do this at city level and link it with these firm ownerships, and we are basing this on the data from the Office for National Statistics on productivity, and we are trying to link it with the same categories of products. So thank you very much. I would like to draw your attention that I would like to acknowledge the funding of the EPSRC grant, which is written here above, and also all the Urban Dynamics Lab team at UCL. And if you want to look at this paper, which is sort of work in progress, it is here in the above link in the archive. Thank you very much.
Thanks, Natalia. That was fantastically interesting. I actually have questions for discussion later, but we will save that. Our next speaker is Nikita Sinitsyn. Nikita, right? Hi, Nikita, we can't hear you.
Good afternoon.
Good afternoon. Take it away.
I'm a PhD student from Lomonosov Moscow State University from Faculty of Geography. And essentially, my study is about clusterization of users from the most popular Russian social network, which is called VKontakte. It's really popular in Russia. It's more popular than YouTube, Instagram, and other widely known social networks. So what about research design? My data was downloaded from VKontakte via its API. All personal data in contact hierarchy are open and everybody can download it for its own purposes. What is the main subject of my work? What is a network behavior pattern? It's a group of users with similar but not equal subscriptions. It's very common with types of cultural consumption. Culture consumption, it's a term from Pierre Bourdieu's distinction. He identified it as a set of practices which reflects individuals' tastes and interests, such as TV programs, books, songs, and so on. So it's consumptions of some cultural things. And my hypothesis is the following. Is there is a correlation between structure of cities' network behavior patterns and social and economic characteristics of these cities? A little bit more about research design. First of all, I collect the list of subscriptions from every contacted social network user from urban settlements of Vologda region. The second step was to represent collected data as a graph. The vertices are users and public pages. The edges are subscriptions of users for some public pages. Then I perform the graph clustering. Clusters will be groups of users which tend to subscribe for certain sets of public pages. Such group was named as network behavior patterns. Then I plot some maps to understand the factors of its spatial structure. It's a little schema of data processing. User data collection. I collect, first of all, I search some of all users from major urban areas of all the region, which age is about between 15 to 70 years old. Then I filter fake users. I implemented 3 filters. The first filter is a filter of 2 weeks. The second filter is a filter of great number of followers. And the third filter is a filter of status, because some users which are fakes tend to place some ads in their statuses. The third step of data collection was downloading of user subscriptions. I want to mention that only open users pages could be downloaded from API. The total amount of users pages is about 32% of whole population of Vologda region with the age from 15 till 70. Construction of the graph. On the right side, you can see a little schema which illustrates a tiny example of my huge graph. It's an age list, so there are 2 columns, publics and users. And then from such a table, I create a real graph using R. All data analysis was performed in R. What about instruments? First of all, I lay out this graph using force-directed layout with the help of algorithm which called OpenOrt. Then I filter some noise vertices uses dbSpan. The third step was to identify cores of clusters simply using hierarchical clusterization. And the fourth step was to classify peripheral parts of clusters by k nearest neighbors. Here you can see layout of my graph. As you see on this picture, clusters are really well defined, and they look like real clusters. It's not my fantasy. So what about types of clusters? Clusters and patterns are it's the same subjects. I defined two types of clusters. The first type is H6, and the second type of patterns I called thematic. H6 clusters, the content of publics from H6 clusters correspond to the age and the sex of typical cluster users. And the plot, the context of public pages from thematic clusters has one or several main topics. So on this picture, you can see that H6 clusters are well populated, and over 95% of all users in my sample belongs to H6 clusters, and only 5% of my sample belongs to thematic clusters. We can consider H6 clusters as a mess, and we can consider thematic clusters as an elite, so-called. It's a very rude division, but why not? So let's assign every cluster on the layout, and you can see that thematic cluster situated at the top of the layout, and H6 cluster situated in the right corner of the layout. And in the bottom of the layout, you can see some clusters which are not assigned. There are some clusters of fake users. My fake filters are not bad, but they didn't filter every fake user, but we can extract not filtered fake users using these clusters from layout. So a few words about every cluster. H6 cluster woman, the typical age is about 40 years. Most popular topics of top cluster publics are women's humor, housekeeping, relation and love, cooking, healthy lifestyle, and users of this cluster tends to concentrate in cities of Poland region. Pensioners, the average age of user in cluster is over 50 years. Users from these clusters are interested in woman humor, news, cooking, health, housekeeping, and dacha. They tend to concentrate in townships. Men's cluster. The average age of men of user is over 35 years. Users from these clusters are interested in men's humor, cinema, automobiles, relations, and love. And the share of this cluster is equal in city of every population. Pupils. Pupils are very young, as you see on the population pyramid, and they are interested only in children's humor, school humor, funny videos, girls' humor, and so on. And they tend to concentrate in townships. Girls. They are also rather young. The average age is about 19 years. Most popular topics for users of this cluster are girls' humor, pop culture, beauty, cinema, and esoterics. They also tend to concentrate in cities. Guys, guys are interested in youth humor, football, news, and moralization. They tend to concentrate in cities, and their average age is about 20 years. The next type of patterns, thematic clusters. First of all, let's look at the creative class. It's a male cluster with average age of user over 35 years. Users from these clusters are interested in sci-pop, news of culture, music, design, and programming. Typical portrait of the member of creative class person. And they obviously concentrate in cities. Gamers tend to games. The average age of gamers is about 20 years. They are interested in computer games, computers, cyber sport, and anime. They tend to concentrate in cities. Anime lovers. It's a female cluster, rather young users, and they are interested in anime, painting, astrology, and K-pop music and culture. They are also concentrate in cities. The last cluster, no, it's not the last cluster, footballers and rappers. It's a male cluster, also rather young. They are interested in football, moralization, rap, and cynical humor. They tend to concentrate in cities. And it's really the last cluster, low-born fellas. It's the only thematic cluster which tend to concentrate in townships, not in cities. And users from this cluster are interested in automobiles, music, and erotica, the typical portrait of guy from blue collar rock. So what about geography? I've told about sociology and data analysis, but what about maps? Here is a map where I show the diversity of network behavior patterns of urban settlements of Volga region. What we can get from this map? First of all, the share of citizens that use Kontakte is proportional to the population of urban settlement. As you see, it's over 35% in cities, and it's over 20% in townships. And in middle-sized cities, is over 25%. The next, what we can get from this map is following. The density, the diversity, which I measured via Shannon entropy, is proportional to the population of urban settlement. Let's look at some schedules about diversity. What we can see here. In the left corner, we can see dependency of diversity from the number of users in urban settlement, and it's very close to logarithm. On the right picture, we can see some points. It's a scatter plot with a trend line. We can compare the position of every point with the trend line. What is important here? For example, let's look at the cities. Volga is a city of central functions with developed mechanical engineering, informational technology, and so on. And the model, it's simple linear model. estimates its diversity a little bit lower that it is. But Cherepovets, which has the same population, has a little bit lower diversity that the model calculates. It seems to me that the reason is in its specialization, because there are no creative industries, only ferrous metallurgy and production of mineral fertilizers. So the same situation is about other types of population. For example, middle-sized cities. Veliki Ustюг, which is the homeland of Russian Santa Claus, has higher diversity than Sokol, which is a typical industry center fulfilled with forest industry enterprises. And its diversity is much higher than Sokol's diversity, is much lower than Veliki Ustюg's diversity. But their population are literally the same. And the most interesting case is townships. There are two types of townships. From the one side, there are Vytegra, Gryazovets, and Babaeva, and they lie up to the trend line. They have high diversity, and they are not industrial centers. They are centers of services, especially some transport services. But some other townships, for example, Karduy, Sheksna, and Harovsk, lie below the trend line. And they are specialized on forest industry, power generation, and penitentiary system. So you can see the different specialization gives us different diversity. And the diversity of patterns depends not only on the population, but also on the role of the services in the local economy. It's a very interesting conclusion. It connects some economic features with cultural features. So let's to sum up a little bit about conclusions. The fake user filter of Kontakte social network was developed. The complex user characteristic was constructed. It reflects its states and interests according to his or her subscribes for social network communities. 11 patterns of social network behavior was defined. They can be divided into groups, age, sex, and thematic. Communities of age, sex patterns have no common subject. They have large number of users. They contain a lot of humorous resources. And communities of thematic patterns have one or two common subjects. They are much less populated, and they contain a few number of humorous resources. The diversity of social network behavioral patterns within the urban settlement is directly proportional to its population. And the diversity of pattern depends on the role of the services in the local economy for urban settlements with a comparable population. So that's all. Thank you for attention.
Thank you, Nikita. That was a fantastic presentation. I am going to move us on because I want to save questions for the end. Next, we have Robin Cura, who I can see is anxious to get going. Nikita, would you mind closing the share screen? And then between us, we can move on. let's think. Robin, hey.
Yes, hi. Second, do you see my screen right now?
Yeah,
Okay, I don't, but I think it's okay. Do you hear me well?
yeah, audio is good, visual is good.
Okay, so thank you. I'll begin. So, hello everyone. My name is Cura. I'm currently a postdoctoral fellow at Geographicité Lab in Paris, France. And I'm presenting a project that I'm kind of starting within the records project that I will present later. My presentation is a methodological presentation named Leveraging GeoIPs as a source of understanding and comparing infra-regional spaces. So for a starter, you might guess what's an GeoIP or what's an IP-based location. So that's, to be simple, it's the way to convert an IP address, which is an internet protocol address, towards geographic localization. How does it work? Because I think it's the main interest here. The idea is that when you connect to internet, you have to go through your internet provider, which disperse connections through network centers that are dissolving connections to local neighborhood small network centers. And in the end, you connect to your internet box and you have access to internet. So how does an IP work? The idea is that every internet provider has access to a range of IP addresses. And that in a simple way, it's simple but biased. Each of those infrastructures are made of sub-ranges of IP addresses. So for example, if you have access to 145.50 addresses from Orange providers, you know that all the IP addresses in your neighborhood will be 145.56.47 and so on. So that's the idea. And the second idea is that when you know that an IP address is within a certain range, here, for example, this range, you know that it's mostly in this area. And if you have access to more detail on the IP address, you can know that it's this area. So if we know that you're connecting from an IP address that is 145.56.47. something, we know that you are mostly inside this small area. So that's a very simple view of how this works, but I think it's important. This allows to localize most IP addresses at the country scale or at the city scale within the whole world. Does it really work? So for a starter, we used those GeoIPs because we're running interviews, qualitative interviews with people, and we had access to their logs and so to their IP addresses. We used those locations to detect some examples, like here, some travels. With this user, we could so see that this user had obviously been to Australia, had obviously been to Cambodia or Southeast Asia, lived in France and went to Spain. So it was an insight to conduct more precise questions. We could also detect some temporal changes, like this user that were mostly connected from Limoges in the central France region until 2019, and that went mostly connected from Bordeaux and the west of France region in 2020. That means, or that might have been a hint that these people moved away. And finally, we also were able to detect patterns where a user was always connecting from different places, depending on the time of the day. So here, it was mostly on the evening and on the morning and on the night. And here, during work hours, so we could infer that this user lived in this area and worked in this area. The problem with GeoIPs is that it's kind of too good to be true. In this example, we have a user that were mostly living here. So all the nights connections were done here. All the weekends connection were done here, but the daily work time connections were done from this place. The problem we had with this user is that when we interviewed her, realized that she never went to Paris, also being localized here like most of the time. So GeoIP is not always very precise, and this is why I think it's has a bad press, and it's very few used among the geographers. So what are the big biases of GeoIP? The first bias is that depending on the type of internet access that users are using, the localization can be very different regarding the precision. Here we have 3 maps. The first one is a map of all the localizations of the users of a musical streaming company within 1 day. So that's made of all points that we are supposing to have users there. Those users are using only cellular networks, so from their phones or from their tablets with 3G, 4Gs, and so on. The second one looks very alike and is made from the cable connection that I call LAN, that is at home using your Wi-Fi network, using cable networks, using fiber optics, and so on. And although those 2 maps looks very alike, we can see in the third map, that is the difference between these 2 maps, that when using cellular networks, you have way less precisions than when using LAN networks. Here, all those points that kind of draw the map of Europe are points that are not available when using only cellular networks. So first of all, depending on how you access to internet, you will or will not be correctly localized. The second problem is dependent, without of the way you connect to internet, is dependent on your internet provider, be it through a cellular or a cable network. Here we have maps of the main French internet providers and all of their localization for a month of data, I think. What you can see is that, okay, those ones are quite precise. Also, this one seems to have less precision than those ones, but the big problem is there, where you have one major provider that localize all his users in Paris, and this one who localize his users coming from all of France, of course, only in certain cities, and so lacks a lot of precision regarding the geolocalization. So to address it and be able to still use GeoIPs, we run an experiment using what GeoIP providers can call the precision of the inferred location. So how do we locate a user? We use commercial, mostly databases, that is like MaxMind or IP2 location or Neustar, etc. And they do provide an accuracy radius regarding the geolocation returned for each IP address. This accuracy radius, in our case with MaxMind, can vary a lot. So from 1 kilometer to 1,000 kilometers, which is a lot. So to test it, we use the semi-ground truth dataset, which is a panel of 1,000 users that did previously answer a web survey about their musical practices and tastes, that did agree to let us analyze their streaming logs, and that also declared the home postal code. So in the next slide, I compare the distance between what the GeoIP location tell us about who people are or should be when they connect to Deezer, and where they declare to live. Of course, it's largely biased because we have no idea if the user is at home or not when listening to the music. But this is a plot that summarizes this information. And there are two main important things, I think, to realize. First of all, the main point is that when using cellular networks, the users in 93% of the cases can only be localized within 100 kilometers up to 500 kilometers. So for a country localization, it's quite good, but for infra country and even a regional localization, it's not possible to use this information. But the other thing to notice here is that when using a cable connection, so DSL, optical fiber, and so on, 75% of the streams are located within 20 kilometers radius around the inferred location. So that's the main point here. Another point is that when you look at this part of the plot, you realize that max-mind communicated precision, which is for those IP 1 kilometers precision, here 5 kilometers precision, and here 10 kilometers precision, it mostly fits with what we measure of the distance between declared home location and the distance where the stream occurred. Of course, it's biased because, I say it again, people don't have to connect from where they do live, but the orders of the magnitudes are quite good here. So we can think, we think that we can trust this information given by this commercial database, and it's kind of lucky because if we look at the cumulative share of IPs given their estimated accuracy, we can realize that like over 50% of the users of a country are located within 20 kilometers radius for most countries. It's not true for Switzerland. It's not true, of course, for the US. And the US is a peculiar curve, and I think it's mostly interesting because it works quite bad in the US. And I think it's one of the reasons that GeoIP is not used much by geographers, because the most literature on the IP location is done in the US. So it's quite a nice source of information, of spatial information. And I will just disclose two cases that I started working on. The context of these cases is inside the Records project that I'm part of. That is an interdisciplinary project that aims at better understanding the content consumption on musical streaming platforms. And we have access to one of the music streaming companies, that is Deezer, which is the biggest in France, not worldwide, but the biggest in France. They give us access to anonymized listening history datasets of all their users. So that's around 1 billion streams per day over the past 10 years. So that's lots of data. We also have access to thousands and soon tens of thousands of web surveyed users about their cultural practices, musical consumption, and some contextual socio-demographic informations like their level of study, their revenues, and so on. And we also run interviews with 100 respondents of this survey to have a more qualitative information on what on their answers. So the first use case, and I will be quick, the first use case is using GeoIP as a way to specialize cultural behavior. Here, I did focus on the way users, people listen to music and to what they listen. Here, what I show is that I did aggregate the GeoIPs that were precise enough, that is 1 kilometer and 5 kilometers, to a French administrative unit, which is the canton, which is kind of like this size. Also, you can see it's a lot of varying regarding the sizing. And I did aggregate users located here regarding what type of musical genre they do listen to. With a simple k-means clustering, after that, I made this map, which shows some very typical informations about Paris area, because it's Paris, which is that Paris and the west suburbs are quite different from the others, way richer, more educated, and they do listen to way less hip-hop music and to more rock, pop, and electronic music than elsewhere. We can also figure out that some of the poorest areas in this region have their own clusters, listening to more hip-hop music and to less rock and to less pop music than the rest. And also that there seems to be a gradient within those practices. So those are the green, red, and orange colors clusters here. The red one listening just to a bit less hip-hop and to a bit more pop. So that is more mixed socially. And the orange one listening to way more hip-hop and way more rock and way less rock and way less pop, which is very the poorest areas of the Paris region. So that is just an example of what we can do without any statistical information, just using the logs of the users. Another example that I think is more important is not related at all to musical consumptions, just to show that although those are the logs of musical streaming services, we can also use this data to show some other things. Here I just made some maps and some calculations of the users moving. What do I define by moving? It's just on a single day, I count the canton in which each users are, and when they move away, so when they change their IP and change canton, I draw an arrow that I don't show here, just the results. And it's very interesting, I think, because it shows in the middle it's Paris, around it's the close suburb, and it shows some very known fact, that is that, okay, Paris is a bit attractive, so more people go to Paris than live in the early morning. Without the whole morning and until noon, there are more people coming to Paris. And in the afternoon, less and less, and in the evening, the soul is negative, which is more people leaving Paris than going to Paris. This is very obvious, of course, but this is, I want to recall it, this is done with the music streaming logs of users. And the main idea behind this presentation is to show that although this is one peculiar service, and I will show this slide. Also, this is one peculiar service with any large enough time-stamped location dataset. We can run a geographical analysis on like anything. And GeoIP, I think, is a very good source of information because, first of all, IP addresses are pervasive. As Kitchen said, you let your IP address whenever you go to internet, whenever you use a device connected to the internet, whenever you use an application on your smartphone, and you keep disseminating it all over the internet. So using those IP addresses is a non-invasive way to gather spatial information about a large sample of the population all year long, so 24 hours a day. Another point is that a fair share of IP addresses can be located within 20 kilometers radiuses, which is a very nice source of information for infra-regional geographical studies. Whatever the country, it's kind of robust regarding the different countries. And finally, that you can partner, and you should, I think, partner with any medium or large internet website or internet service, because they do gather thousands or millions of IP addresses per day, which gives a very valuable source of information on any geographical analysis. So that's all for me. Thanks for listening.
Thank you very much, Robin. That was wonderful. We have one more presentation before we go to discussion and close off this special session, and that is from Roberto Ponce Lopez, Diego Fabian Lozano Garcia, Sebastian Fajando, Alicia Landin, and Pedro Acervo. Is one of you in?
Yep, that'd be me.
Hi, Alicia.
Can you see my presentation right now?
Yeah, it's showing well. I can hear you well.
Okay, perfect. So thank you, everyone. We're going to be presenting the economic cost of urban sprawl approximated by the cost of maintaining road infrastructure in Monterrey, Mexico. This is an investigation that was led by Dr. Ponce Lopez and Dr. Lozano Garcia, as well as Sebastian Fajardo, Pedro Pacheco, and myself, Alicia Landin, as part of TEC de Monterrey and Fundación FEMSA in Monterrey, Mexico. So first, I would like to give a little bit of context to our research. The Monterrey metropolitan area, or colloquially known as the city of Monterrey, is the second largest city in Mexico. It is composed of 16 colliding municipalities and has historically been a large industrial city that is now transitioning towards a more diverse commercial, financial, and service center while still maintaining its industrial base. So here in this slide, we can see a map of Mexico with a little red dot over there outlining the city of Monterrey. As we can see, it's in the northeast quarter of the country. It's pretty close to Texas, pretty far away from the dense Mexico City area. Now, the city of Monterrey has seen a very interesting growth dynamic in the past 30 years. The urban surface has had a growth of 278% between 1990 and in 2019, while population has also grown, but at 168% in that same period. So this has accounted for a very drastic population density decline of 39%, which has been the result mostly of unorganized sprawl. And I believe it's also important to mention here that the city has a very particular set of physical constraints to growth, as we can see in this map, because it's completely surrounded by mountains, except towards the northeast. So this means that any urban expansion that's taking place has developed mostly in very narrow corridors rather than in a uniform grid. So there's no existing accurate records of the city's pavement surface. So what we set out to do was to calculate this network of road surface by building a geographic database with the center lines of existing roads and the polygons that were delimiting sidewalks or property lines within the city. And then what we did was compute the width of the roads using ArcGIS. So we estimated the average and median width of every road. And then we were able to see some very interesting differences depending on the age of the road. So in general, and as is expected, older roads tend to be narrower than newer roads. So this can then be seen into a pattern where municipalities located in the peripheral area, such as we can see here, El Carmen, over here, Garcia and Juarez, which are, again, peripheral municipalities or newer municipalities. They have seen recent growth, have much wider average road widths, much wider roads than the original Monterrey municipality, for example. So this process resulted in a little bit over 195 million square meters of paved surface in 2019, which we then classified into 3 different categories that would approximate the intensity of use of each of these roads using the road width and a current road classification. And through this, we found approximately 31 million square meters of primary roads, 36 million square meters of secondary roads, and almost 128 million square meters of local or tertiary roads. Now, some municipalities have no primary roads, Solo, El Carmen, Salinas, Victoria. Again, these are some newer incorporations to the metropolitan area. these have followed the development model of rural towns. So the paradigm of road setup there is a little bit different from the urban or the city center, and more historic municipalities. Now, once a payment surface was precisely estimated by type of road, our team conducted 17 in-depth interviews with infrastructure civil servants and payment experts to learn about what the costs and common practices of road maintenance in the Monterey metropolitan area were, which we then validated by, again, in-depth interviews with 4 private developer professionals. We identified 3 types of main preventative maintenance processes: surface patching and crack sealing, deep patching and crack sealing, and crack sealing for hydraulic concrete. And in addition, the pavement specialist detailed 10 different pavement surface maintenance treatments that should be occurring, to which they assigned a specific cost per square meter, as well as a frequency of intervention depending on the type of road, whether this is a primary road, a secondary road, or a tertiary road. So using this information, as well as averaging for current common practices, which are very different from the ideal maintenance cycles, we managed to compute what each of these roads, the maintenance of each of these road types is costing. And then this integrated it into the network analysis to discover that in an ideal scenario, maintenance occurring every 3 to 5 years would cost a lot of money. So under current maintenance scenarios, which is maintenance of every 5 years for primary roads, every 15 years for secondary roads, and every 50 years for tertiary roads, the annual pavement maintenance in the Monterey metropolitan area has a total cost of 3.9 billion Mexican pesos. This represents 17% of the municipality's annual municipal expenses. Under the ideal scenario in which all roads receive maintenance every 3 to 5 years, this process would cost up to 11 billion Mexican pesos annually. So this is a 286% increase from what we currently see, which is a very lacking scenario of road maintenance. Now, of course, it's also very interesting to note that there's drastic differences in the conditions of road and pedestrian infrastructure between the city subcenters and the peripheric residential areas. So this 3.9 billion annual pesos is not being reflected into road equity within the city. The current growth model, which is basically unorganized sprawl, is unsustainable both from an economic and social perspective. We have not yet explored the environmental implications of the model, but calculating this 17% of municipal annual budgets exclusively for road maintenance limits basically every other municipal expenditure and social expenditure. We believe discussions of future city growth, considering this, have to consider financial, social, and ecological impacts of sprawl, and look into new models of growth that take these municipal expenditures into account. So again, we presented the situation in Monterey, Mexico, but this development model has been present virtually in all Mexican cities in the last 50 to 60 years. And the budgetary and social implications of this situation are of major concerns both to government and societal actors. So we hope that these analyses can give way to science-based urban policymaking in Monterey, across Mexico, and in other similar development models. Thank you.
Thanks, Alicia. You have some time left if you have anything else you want to say. But if not, I'm happy to move on. That brings us to the discussion portion. If anyone has any questions to ask, we have 20 minutes now in which you can discuss everything we've just heard. The floor is open, so just unmute yourselves and say something. Or if you'd rather be structured, you can message me and I can ask the question.
I have a question. Can I ask the question?
Yes, please.
Yeah. So first of all, thank you very much for all these interesting presentations. I have a question to Robin. I was wondering if, because you were mentioning all these biases that can be are presented because of the internet connection and the way we connect to internet, right? But I was also wondering how does Deezer collect the data? Because I remember your work, Robin, when you were collecting data from Google Maps, and there was a certain bias on the moments where they were collecting the data. So how does Deezer deal with this? Is it anytime someone is connected to internet, or do they have some periods when they record the geolocation? So that was my question.
Do I answer right now?
Yes.
Okay. So the Deezer is a streaming service, and so they do log an IP address with a lot of context. Each time someone use the application or the website to listen to music. So each one you listen to one song, you send your IP address, because you have to use your IP address to collect the music file. So you send your IP address each time you listen to any song, along with information on the device, on the type of connection, of course, on what song you're using. Of course, what's the context? Like, are you listening this song from a playlist, from a search, and so on? So it's really volunteer based on each action with the Deezer streaming app. So we don't have information on whole day long logging, but for active users, we have like 2 hours a day maybe of information, and this is like almost every day for most users, almost every month and almost every year for the past 10 years for some of our users. So it's not a total logging, but it's already a very precious source of information, I think.
Right. And may I ask another question? How do you link the quantitative and the qualitative part? Because you have, I suppose, individual IDs, and then how do you look up for these people? Do you have some consent with Deezer about this, right?
Yes, we are. First of all, we ask our users for their permission to look into their data. And I'm kind of an external researcher with Deezer. So I have access to all the databases, in fact, all the production databases of the users. And so I can just look inside the databases for all of the logs of the users, given that they did accept for me to look into. And that's another work that I don't present at this ECTQG, but I did develop an application that is used by my colleagues, my sociologist colleagues and so on, to run the interviews by mixing the users' qualitative answers to the survey and their logs analysis, so with lots of geovisualizations and data computation, so that both information can be mixed. But that's another topic.
Thanks.
We have a quick question for Robin from Aleksey chat. What information are used for geo-IP by services? The IPs are not enough. They mostly are dynamic. They reflect the same devices every time. What do you use for geo?
Okay, it's not my specialty, but I can give some first simple answers. Of course, IPs are dynamic. That's why when you're using geolocation, you have to use up-to-date databases, which is that most producers produce one database per week because IPs are changing. They rely on known information, mostly provided by internet providers that for some time say, okay, this range of IP addresses is in this area. So that's passive information, and they also rely on active geolocation, which is by pinging, by triangulating different IP ranges. They infer location, and it's of course a big commercial issue. I don't have the method they use because it's millions of dollars in this business. But I would love to know more about it. I know what's being done within the state-of-the-art research. That is like using Wi-Fi networks together with just like Google does to precise the location. That is also by crossing information on the IP addresses and on the user digital footprints on different services where they do let their locations. So that's a lot of combinations of methods, I think, that I say it again, I'm not an expert of because I don't work for such companies, and that's it's mostly very secret because very business competitive. And it provides quite a good information. So that's a very state-of-the-art in computer science and in computer networks methodologies.
Aleksey, does that answer your question?
Okay, thanks. And I only want to note that I'm a bit envy about your level of access to the data, personal data, because we have something in common. You try to geolocate people using internet connections. I'm trying to do the same with mobile phone connections, and we are not even allowed to get access to these databases. We are not allowed to see on the screen. I wrote some code, sent to people in mobile phone companies. They check it, run, and then they send me results. Even it can be not meaningful results. Then we repeat this process. So it's very complicated when mobile phone companies are very suspicious about all this studies around geolocations and positioning. Okay, thanks for your answer.
Robin, do you have anything to say to that? Or...
I will be answering in the discussion in the chat.
All right, fantastic. In that case, I have a question for Natalia, because the North-South divide is something I'm very interested in. May have answered this in the actual paper, but I wasn't sure about the presentation. It seems like you've identified a lot of trends and a lot of difficulties in the economic divide between the North and South of the UK. Does your report make any recommendations, or is it an identification, sort of more of an exploratory report?
Well, the recommendation would be that this policy would be really working, right? But I mean, it was just the objective was just to make an assessment, right? like a state of the art and what's happening at the moment. We don't have access to more recent data, unfortunately. Well, we have 2018, but it's, well, so we are in 2021. There's Brexit and coronavirus that happened in between. But well, I think it's an endless problem, this north-south divide, and the recommendation would be to, in fact, to try to reboost these interactions, or at least the economic weight of the northern cities. And I mean, it's not like these are important cities, and they are. If we think about Sheffield, a lot of people are leaving. This young people are leaving for London. So there's a lot of issues. But I mean, I think it's more about the government that should be, investing more in this kind of public policies, also at the greater, at the greater authorities level, like Greater Manchester Combined Authorities or other. Kind of organization of this type, but also, I mean, I would say it's an endless problem, but I think it needs to be done from a centralized system. But I think the UK system is not really, government leaded, and also each time a politicians come to power, they put this on the table. They put this topic on the table, but it's never. I mean, it's never really realized. But I mean, when the coronavirus occurred, I think there was a lot of things about the fact that London might lose some weight because people can work from home in Sheffield or Newcastle, wherever. But I think, well. This divide will continue, and it's a huge problem in the UK, I suppose, and maybe you also kind of feel it because of being in Manchester. I don't.
Thank you for that. Does anybody have any more questions for anyone at all? They don't have to be about research. You can just ask how they're doing. No?
Well, I had a question for Nikita, if there's still some time, about his presentation about Kontakty in Russia. I just, maybe I missed a bit in your presentation, but I was just wondering, why did you choose Vologda region for your study? So did you apply this for your whole analysis, or it was just at the end where you were comparing it with the population size? And do you think that taking into account, for example, other regions or the social network, your results would be different in terms of, for example, taking into account Moscow and St. Petersburg would be different in your results in terms of these different trends? I don't know if Nikita is still here.
But you are muted.
I'm sorry. Everything okay? Yeah, thank you for the question. First of all, about the region. I choose this region because it's my little homeland and I know it very much. So I decided to use it as a case study for the beginning of my research. It was a beginning part of my PhD, and now I collect all data from all over Russia, every user which is open in Kontakty. And now I perform the same analysis using C++, but my big data skills are not so keen nowadays. I try to do something else, and it seems to me then in the beginning of the next year I will do the same for all over the Russian cities, villages, St. Petersburg, Moscow, and so on.
Okay, thanks.
Well, unless anyone has one last question, I think we're good to go. Out of curiosity, if I think a few of you are staying with me for mobility and distance at 11:20. Anyone going anywhere interesting for the next session? That's what you're not, because the only interesting one is going to be mobility and distance with me. So I hope you all have a great rest of the afternoon. If I don't see you, it's been lovely to hear from you. Thank you so much again to Aleksey, Natalia, Nikita, Robin, and Alicia for those great presentations. And I'll see you guys later. Have a good day.